Hello everyone, my name is Jacob Tifo. I'm with alphaomegarocketry. Uh, this is my 8th year in the aerospace program, and it is uh, one of my 10-year projects, or will hopefully be. Uh, what I would like to introduce to you all today is a model rocketry concept. But before I get into that, I would like to say thank you to all of the people that made the 2024 H Fair possible. The club leaders, the project leaders, our distinguished judges, our club members, and the maintenance people, office workers. Just want to say thank you to all those. As I mentioned, I'd like to introduce a model rocketry concept, and that concept is thrust vectoring model rockets. Now, the first question is, what is thrust vectoring? Thrust vectoring is where we want to angle the thrust of our rocket, the engine's output, let's say, and control the rocket to go straight up. Now, we want to get this down to a model scale, and I will explain that in just a moment. But thrust vectoring, as you can see, let's say the rocket starts to tilt or vary off of its set point 90 degrees. The engine will have to correct for so much in order to bring the rocket back into a stable flight path. Now, as you can see, this is only doing it in one dimension. You would need this to do it in the X and the Y dimensions in order to be able to have successful control of the rocket. This right here is a quick video that I found on Wikipedia for thrust vectoring. And as you can see the angling of the thrust output. That's what the red's the nozzle, and you can see this gray area out. That's our thrust, and the rocket is obviously blue. But you can see thrust vectoring in that. Now, you may ask, how do I hope to achieve this? Well, there's a few different ways. There are the PID algorithms, and we will get into that in a minute. But in order to get a set of values and to prove our points, we need to do some basic tests. The first test was to make a data logger for a model rocket. This is our Zeta Generation 1 flight computer. It is just a data logger. We have a FRAM memory chip, SD card module, we have some sensors, barometric pressure, and our gyroscope and accelerometer. And we have our microcontroller. This is my electronics project for this year. So you can check out my other video for that purpose. And we'll dive down a little bit deeper into each one of these components. Our next test will be to conduct a hold down gimbal test. Now, this is something that has not happened yet, but we are very, 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 very close, and we are we are extremely excited for it, as you can tell. This is our mount. This is what we will be gimbaling. I actually have one right here, and it is a mount where we can control it in the X dimension, and we can control it in the Y dimension. And that gives us a full range of motion to be able to guide this model rocket. For anyone with a 3D printer, you can download our thrust vector control mount, that's what it's called, on Thingverse, and you feel more than welcome to do that. Now, the way we can intend to control this mount is using 9G servos and a special mathematical algorithm. The algorithm is PID. Now, PID is extremely complicated, and I honestly don't even know everything involved with it. It can get very, very difficult calculus, and I'm not quite at calculus yet. Soon, though. But to put PID in a nutshell, an extremely small nutshell, we can break it down into what each of those components mean. P stands for proportional, I stands for integral, and D for derivative. Proportional are actions that are being conducted in the instantaneous moment, in the present. Integral is a collection of those instantaneous moments and is in the past. The derivative is a proportional to integral ratio that aids in correcting for the future. Now, the value that we are calculating is not necessarily straight sensor data, not like 90 degrees or 89 degrees or 92 degrees. It's nothing like that. We are calculating the error off of a previously set point. For example, that would be 90 degrees. So if I were to go back wrong way. If I were to go back to here, this is our 90-degree set point. And if it varies off of this gimbal angle, A, is an amount that is off of our set point. That's the center line, that's our thrust line, that is the error. So back to here, that is what PID stands for. We are calculating the errors, and then we'll be able to write commands via code to servos, which will then move our gimbal to correct. Now, as I mentioned earlier, that was an overly simplified PID explanation, and it can get a whole lot more complicated. If you'd like, you can check out my YouTube channel, alphaomegarocketry, and I'll have on there some more control theory videos, not mine, but other people who are a whole lot smarter than I am. And if while you're on there, you can check out more of my YouTube videos. We're going to be having a somewhat detailed trail of videos as we work towards our thrust vector control. And if you'd like to learn even more, you can check out my website at alphaomegarocketry.space for some other cool stuff. But I want to thank you all for tuning in, and want you all to stay safe, enjoy the fair, and want you all to have a nice day.